So those moments, just a moment. Those moments, what solution. Wait, I'll try to find size. No, sorry, I think it's the only size I can find here. So solution, what should be when we speak of solution, we always should take into account which exactly questions are we asked. I have no idea where is this word now. Okay. So we need to present exactly the answer to the exact questions which we read in the task, right? Like no doubts, but still not everyone does that. So that means that like it's worthwhile to recalling. Okay, and so we need to satisfy the goals of the task, right? So if the task contains finding an answer, then definitely then the answer should be the first and probably the main part of the solution. The remaining part is just an explanation why it is an answer, or why it is the answer, because usually we should write down all the answers which are supposed in this problem, right? So we should, speaking of a structure of a proof, we should start from an answer, and after that we should write down the explanation. And what is the explanation? Okay, I don't think I can fix it. Okay, so answer usually is the most understandable part. So if you solve sort of equation, you understand that you understand what is an answer to this equation. If you solve some sort of combinatorial problem with a question, what is the answer? What is the number of I don't know, permutations of combinations of something? Usually we understand that we should come up with a number which is exactly the quantity of the objects which we are counting, right? And usually this is a very clear part. But what is not so clear, what is an explanation for it? And explanation for it, it is a tree-like looking structure where this given part, meaning conditions of the task, like the word goals went, it just misses each time. I have no idea where it goes. So the conditions, the target question, of the task as a goal, and here, like, if the question, if the problem is supposed to have an answer, then the target question is the same for all these problems. And like the target question is why is it an answer, right? I hope you remember what I told like a minute ago, that if a problem is supposed to have an answer, then the answer is the first part of the solution, not the very last thing, as it is done oftentimes in school practice, but it is the first thing. When you come to somebody and ask what is the time now, like what time is it, like you don't expect them to explain you how the universe works and what is the invention of Albert Einstein and what is the modern physics thinking of relativity theory and quantum theory and so on. You expect just plain answer, the time, right? And when the problem asks how many options are there to do something, the very first thing which the jury member, the grading person expects from you is the answer, is your analog to 3:15. So please make it clear, like it is the first thing which you should mention when you present a solution. If you're used to an opposite thing, and like me personally, I know that from my school times, like usually we wrote this solution, and after that we wrote down many lines of a solution, and just after that the answer. Like it is just a study process. It is just like it is developed to teach you to write down reasonable text. It's not a right way of doing mathematics. So sorry, like come up with a new habit, like write down the answer first, be ready to present it. So now speaking of the solution, like usually what people explain here is have sort of this structure for explanations, some steps which could explain what is happening in the solution, and some steps actually they could lead nothing useful for the problem. They could bring us to exactly those things which are needed in this problem. So each arrow here shows or denotes one basic step of a conclusions of concluding in this problem, and the final structure of a solution would be something like this. So finally, finally we should find a continuous line of reasoning of all the steps from the very beginning to the very end, which explain how did we get from the given conditions to the final answer, right? Like it's very general explanation. Like I hope you understand, like I hope you know basically all the parts, but I just give you like this broad guidelines, and like that means that sometimes I will repeat things which you understand really well. So what could be one single step of this structure? One step. Basically, one step So what could be used as one step? So there are basically just several types of one step, of single step. So it's implication step, it's calculation step, it's sort of construction, or example step, and one more is sort of assumption, counterexample, assumption, and contradiction. Step. So basically, these are like the main steps. This calculation step is the least interesting of them, because I think all of you understand what is calculation step. So it's not very attractive part. Like you just compute. So this part is clear, hopefully. What is construction step? It is also something like more or less understandable. So it's when you present something new to the solution, right? So, for example, if you solve a geometric problem and you had some particular points, some particular objects given in the task, and you decided to make an auxiliary construction, you should present all the new points, you should present all the new lines which you use, and that is sort of additional step, or some particular step which should be done, because otherwise it's just not clear what are these objects. Sometimes it leads to work like multiple sense understanding of a phrase. So when you cannot decide in which form, in which sense to understand the sentence, and in this situation, jury member couldn't treat it as a clear solution. Sometimes it doesn't cost you any penalty points, but sometimes it costs. So just uniformly understandable phrases are usually considered as mathematical phrases. So just do this part properly. Present everything you want to bring, everything new you want to bring to the solution process. And sometimes this construction step, it needs some additional explanations. So it might need some new definitions, some new like names, tags, and so on. So you need to do all of this stuff in order to like pass your idea further. And the remaining two steps, implication and assumption contradiction, are just two main ways, two main tools of a proof. And basically you know that, but some details oftentimes miss in understanding of different students. So like different moments could turn to be unknown by different persons. So I will again I will tell these matters which probably are known to you. So sorry if it's well known for you. So let's speak of assumption and contradiction step. Basically, it refers to method of proof. What's that? Usually proof by contradiction is used to deal with some impossible cases. Or interesting enough, also it's used to prove in two obvious cases. Two obvious. Two obvious statements. For example, in number theory. So many things in number theory, they look like very, not basic, but in sort of, in some sense, like magic or obvious by itself and so on. So you look at it and you don't know how to explain it, but it's you really understand that it's true. So you start checking and you understand that it's true. For example, very interesting statement that each prime like I will just name it, I wouldn't write it down. So there is a statement that each prime which has remainder 1 modulo 4 could be represented as sum of squares of integer numbers. So if you check numbers 5, 13, 17, and others, like the prime numbers which have remainder 1 modulo 4, all of them are represented as sum of squares of integer numbers. And you check it and you realize, wow, like that's true, like I understand. So number theory, it looks like a bunch of statements which are like, all of them could be used as axioms because they're so true, and like you just cannot do anything with that, just admire. But oftentimes, like, that is definitely not enough for proving that, wow, I noticed, I checked 10 of the numbers, I checked 20 of them. It's not the proof. And oftentimes in this situation, you could use proof by a contradiction. Not in all of them, but sometimes. So proof of by a contradiction, it should start with an assumption. If you have no assumption, you couldn't do a contradiction to anything because you use just conditions of the problem and mathematical like true statements proved before that, like theorems, lemmas, and also axioms, which are not proved but like verified. So you have nothing to have a contradiction with. So if you hope to have to get a contradiction, you need to have an assumption. And if you have an assumption, you should get a contradiction if you have an assumption. Because otherwise, it's just incomplete solution. Why? Just because any assumption, it's like division of all the possibilities into groups. One goes to what is assumed, and another goes to like what is like what doesn't hold with this assumption. So the group which doesn't hold for the assumption, it would be not covered with your conclusions if you don't like if you stay with just an option, an open assumption, and you just cover this this line of reasoning. So if you have an assumption, you should come to a contradiction. So this looks like this looks more or less like this scheme. So it would be yes or no here. Assumption here. And is that you just cross out part of the possibilities here. You just show that this is not the case. That means that just the rest of the situations is exactly the case in this problem, and you go further. And like more or less, it's everything about this assumption control. And the fourth type of steps is an implication. And this is also well known by all the students who like and who do mathematics, but many people do it wrong without knowing how to do it right. So what is right here? So implication has what I call 2.5 steps or 2.5 levels. So the first level is external level. External level of explanation. It consists of 2 parts. A title, like Pythagoras theorem, or Fermat small theorem, and so on. So usually you use this word theorem, lemma, sometimes axiom, for example, angle measuring axiom in geometry. And also what is important here is a clear and of course correct statement. Sometimes this part, clear and correct statement, could be used instead of a title, because some theorems are more famous and important than the titles they were. So some statements could be referred to just by this, like the statement itself. But you shouldn't confuse it with anything else. Particularly, you shouldn't confuse it with your own invention, because in this case it couldn't be called theorem. Theorem is a well-known fact which was proved and published and read and checked by many mathematicians by the moment. And the fact which you proved is called lemma, and it doesn't have any personal name, so it's not theorem. And also, of course, you can use your own lemmas here, but an important part is to have a proof of this lemma before the statement in your text, before or independent from the further part. So sometimes some people write it later. It's not very correct, but like it's possible. But what is important, that you doesn't use anything you so you shouldn't have this these cycles, vicious cycles, vicious circles of statements when you prove something using the fact itself. So the best thing is to write first to prove a lemma and use it just after that. So internal level it is just usage of the statement, of the general statement in this particular case. Like, it's very understandable part. So if you say like by Pythagoras theorem, a hypotenuse squared is equal to sum of squares of the catetus, and that is an external level, and the internal level would be to say, and in our problem we have one cated equal to 3, another one equal to 4, so we have a hypotenuse equal to 5. So we just apply this statement to this particular case. So these are all the basic examples of what step, one single step in this proof structure. Well, what's next? Next thing is the presentation order and presentation rules. So rule number 1 is that there is a right order of steps in a correct solution. So when you come, when you invent your own solution, the steps which you create, the statements which you create, they come in a random order. So you come to your ideas in a random order. You should reorder them in such a way or in the most helpful way. So if you want to earn more points, if you want to get the better result, you should just prepare your solutions, prepare your texts in the best order, in the best way you can, like to make the solution more readable, to make it more understandable, and that's very clear thing, I think. So if you want more points, you should do better, basically. So for this statement here, what do I mean? For example, there is one famous problem, which is like this. For example, prove that AC plus BD is greater than AD plus BC for A less than B and C less than D. How it could be done? Usually people do something like this. They look at this thing, they try something like, well, let's try AC is less than BD, and they realize in some time that oh, it might be not true, not for all the numbers. After that, eventually these people could come up with an idea that that 0 is less than B minus A, and after this they could come with an idea that A times C minus that A times C minus D is greater than B times C minus D. After this, they come up with something like, oh, so we can write down that A minus B times C minus D is greater than 0, should be proven. And here we see that A minus B is the same as here, and we know that it should be greater than, it should be less than 0 because the opposite number is greater than 0. So we ask ourselves, is C minus D less than 0? And here we say yes, because C is less than D. So it is more or less normal solution, but in the same at the same moment it's not, because we confused all the steps here, and also we tried something like unimportant, unimportant. So basically we should cross out this part, we should restructure here, and after that we can come to some nice statement. So this should be changed to this natural order, where you don't change the direction of your thought all the times, because it's just annoying, it takes time to understand, and so on. So it should be changed something like 0 is less than b minus a, and 0 is less than d minus c. So that's why a minus b times c minus d is greater than 0, because if we take opposites to all these two positive numbers, which means that it is a product of two negative numbers. And after this, we deduce that AC plus BD minus AC minus BD is greater than 0. And from here, we deduce the fact which we needed to prove, that AC plus BD is greater than AC plus AD should be here. Okay, I think it's impossible to fix like this. Sorry guys. So it is wrong stuff, and the right stuff is this. So AC plus BD is greater than AD plus BC. And this is exactly what we needed to achieve here, right? So what does it mean? That means that when we create a solution, here we create, and there is a phase when we formulate. Okay, and it means that we should take this into account, that there are two different phases. So if we start creating exactly to our white paper, that means that our solution would be always with some mistakes, with some strange order of things. So it would be all the time not perfect, not well done, but oftentimes it would be worse than it could be. So this means that when you write down a solution, white paper, and this should, and that means that you should have scratch paper and white paper different in different on different papers. And also that means that there is some natural way of showing a solution. So this solution could be written in an opposite way. So oftentimes inequalities are done in an opposite order. So you might write down a solution that this inequality would be true if, and after that you can write down this inequality and say if this difference is greater than 0, this difference is greater than 0 exactly in those cases and when this product is greater than 0, because these are two equal numbers in different forms, and this product is greater than 0 because it is a product of two negative numbers. So if you write down this solution in an opposite way, it would be also okay. But it's not the same as writing down all these steps in a random order with different pieces in different places. So it's not a good way to write down a solution. So use the correct order, and oftentimes the correct order is exactly the opposite order than it was on a scratch paper. But usually it's like a bit more twisted. So some statements go in right order, some statements go in an opposite order, and you should just prepare it well when you transfer it to your white paper. Okay, and the last thing which I wanted to mention is another presentation rule, sort of general one, which is valid not just for mathematics. It's text structuring. When it goes to text structuring, oftentimes it's also a big point of mathematicians, because mathematicians are mostly focused on coming up with this insight, with the idea, with the correct statements, with the examples and counter-examples, but usually not with the correct or not with an effective presentation words, not with an effective presentation phrases and presentation patterns. So if you have a large, like mostly it refers to big texts of solutions, but also it might be valid for medium-sized solutions. Like very short solutions could be read in any order usually, so it's not a problem. But if it becomes larger, it might be troublesome. So what I'm speaking of. So a thing which is sometimes called Hemp Structure is welcome, or more than welcome, when you write down a mathematical text as well as any humanity sciences text, or like any general text. So what is Hemp structure? Hemp structure is very intuitive and simple stuff. It says how to structure a single paragraph of your solution. And basically it's very, very intuitive. So imagine you telling short story. When you're saying this short story, you start from some introduction. And for mathematics, that is exactly answer to a question, what we do here. What we do here. After that, we have a big chunk of hopefully interesting and tasty enough. Not very big, because otherwise it would be. And after that, we will have sort of final part, the conclusions of what we done here. So introduction, some words about what we do here. The middle part is we do, and here conclusions. What and also what follows. So it's like conclusions and relation to the further part. The text here disappeared some. What we do here. So basically, this is the Hemp structure. So we do some intro. After that, we do what we promised, what we just promised. Like, I have no idea where this text disappears. Okay, we do. Okay, now it is what is hemp, exactly hemp sandwich structure. Ah, sorry, I missed one word here. Not hemp structure, but hemp sandwich. Hemp sandwich structure. Okay, and the final part here is that we use it not just for one paragraph. So it referred to one paragraph, like each paragraph. So your text should be divided into paragraphs. Each paragraph takes around 3 to 7 sentences, like full size sentences. It depends on on how you divide the sense which you want to explain, to transfer to somebody, to some other person. So your paragraph should carry on a piece of sense, of idea. So each your sentence bears a piece of information. Several pieces of information should collect to a paragraph. It should be not very large, to have not more than, say, 10 sentences in a paragraph. And each paragraph should be built sort of this structure. Like, it's sort of ideal structure. So never you do it as this good from the very first shot. So probably your solution wouldn't have exactly this form, but at least if you use a scratch paper a bit, so you make some scratch conclusions on the scratch paper, and after that you bring it to a paper, and if you take into account this structure, like your text will already be better. And what misses now here is what I call fractal sandwich principle. Fractal sandwich principle. It means that this structure. So if you take a big part of solution, a bigger part, if you have many sentences, if you have really big text, then you have a big introduction, which is another ham itself, in another sandwich itself, sorry. And you have this conclusion part. And each of them is also a small sandwich. And basically the rows are more or less the same. So you give this introduction part, you give the substantial part, the main part, you give the outcome, you give these conclusions. And if you have even a bigger part, like it's like it has nothing related to our Olympiad, but like probably you will be writing down bigger texts in your life. So if you have even a bigger text, like the bigger text would have also the same structure, especially if that's a technical text. So you just use the same structure on each stage, and like the ratio oftentimes is more or less like 1 to 3 to 1 or 1 to 5 to 1, like not very big difference in scales, not 1 to 10 or 1 to 20. 10 probably is still possible, but 20 is something. And the very last thing here, so sandwich structure. The very last thing here is that if you want to have really good text, what you can do is write down thesis of the solution. And what are theses? Are basically listing the main idea, the main sense, of each of the sandwiches. So you just take one single sandwich which refer to paragraph, and you can write down the idea 1. For example, in this solution, we will implement like proof by a contradiction, and for this we will suppose that something is like following, and it is sort of introduction. And after that, you show how to perform all the details here. That would be sort of idea 2. Right. Like you might have several steps here, how to do that. It will make up the idea 2, the idea 3. And if you have a bigger sandwiches, usually you do, you have not one paragraph, but you have like more paragraphs. That means that you have at least one more level of sandwich. Then you might write down the general idea of the like of this sandwich, and so on. And this might be useful, for example, for problems for estimation and an example, where you have two separate parts, when you basically write down independently in estimation part, it might have a big solution, relatively big solution, and example part, which might also need some explanations why the example works, and that might be two different chapters of your solution. And that means that on the second level you might have several sandwiches as well, and like you can name the chapters as well. So it would be like chapter 1, chapter 2, and so on. Okay. Mostly that is it. So let me just repeat what we discussed today. So I recalled that a solution, it is a directed line of reasonings. It is a sequence of steps which start on conditions of the task and finish on the goals, on achieving the goals of the task. And the main goal, which could be valid for a problem, is given an answer, but sometimes it's just not not related to a problem, not like not referenced to the problem. Like sometimes, like you just have a problem which doesn't suppose any answer. In this case, you definitely you shouldn't give an answer in this case. But if the answer is supposed, then the answer is the main goal. And the second goal is explaining the answer. So to give a solution means to give a sequence of steps which bring you to the solution, like to the final stage. And there are just several types of steps which you can have in this structure. Like generally, we can list 4 types of steps. That is like implication or direct proof step. It's calculation when you do some arithmetics or when you do some arithmetics. Another type is construction or example step, when you bring sort of a new structure to your perspective, to the scope of your consideration. And another type is assumption contradiction step, which is like backwards proof. So when we speak of proof by a contradiction, these 2 steps are absolutely necessary. It's assumption and contradiction. So without an assumption, there couldn't be any contradiction. So if you didn't state any assumption, but you came to a contradiction, you should come back through your solution and find the place where an assumption should be done. If you made an assumption, or you started considering some particular examples, for example, then you should come to the moment of the contradiction. Otherwise, it's also just a partial solution, because you will have a branch of, or you will have a set of cases which were not considered by your conclusion, in your conclusions. If we speak of the last type of steps, an implication step, then each this sort of step, like the most common type of steps, it needs 2, what I call 2.5 levels of explanation. So first of all, you need to name this, name the statement, the general statement which you use. So you cannot say that you cannot just say that something is true in your solution. You should give an exact reason why it is true, and the reason is usually a theorem, an axiom, a basic fact from a school, which was stated not for your solution just now, but which was stated before you know the problem, like independently from the problem. And like just one other option exists when you prove some particular lemma in your solution before this particular moment in solution. So if you proved already something auxiliary, and you just say that it is lemma number 2 of this solution, for example. And another necessary moment in giving a name of the like in this part of explanation is formulating clearly and correctly the statement. And like the second level is an internal level. It is like taking this general framework of external level and applying it to your particular situation. So it's when you apply some theorem to your conditions, to your to the conditions of your problem. For example, like you apply a Pythagoras theorem in some particular geometrical problem. Okay. After that, we went to some presentation rules, and two main rules are the right order of steps in the correct solution. So your steps should go consequently in the order like in which you present the steps. Something strange happened to this, so like it should be done like this. Some text was hidden here, I don't know. Like hopefully you track this during the presentation. So so you should choose the right order for listing the statements which you created, which you come to or come with. Like you shouldn't do too many jumps in the logic of the presentation of the solution. You shouldn't go back and forth all the time. So there should be some clear logic. Either you go from the given conditions to the final point, or you like use your final point as an anchor, and you show step by step like the previous steps which should legislate the next line. So for example, when you say that for proving this inequality, we might use like the previous one when these two terms are in the left hand side, and for proving this inequality we can use this one, and so on. So it's like an opposite direction. And also there is sort of hybrid style when you do this backward stepping, and at some point you just switch to the initial conditions and you do the forward stepping, and the back stepping stops exactly at the same point to which the forward stepping comes. Like it is also like widespread in mathematics. Like sometimes it looks a bit better because you like keep a part of intriguing, like an intrigue part, like in a movie. So will we find will we find the final explanation or not, or something like that? But it's just one switch of the direction. So we went like back stepping, and after that we go forward stepping. Like still okay. Just a second. Okay, our final step was a discussion of text structuring. The main idea is that we use a sandwich structure or hemp sandwich structure to structure the text. So probably the metaphor is more used to, like, is more common to the Western, like what we would say, Western world students. But hopefully you understand what is meant here. So when you have a sandwich, when you have two slices of bread and something tasty in between, and this side in between, it is usually what is important in this block, right? It is the main part of the sandwich. So if we consider any particular paragraph of the text, we have an introduction, or part of the text where we make sort of a promise what we will do here. So we explain what we do here. So for example, let's calculate the remainder modulo 4 of this number. And after that, we do the calculations, and we finalize this block with the conclusion. We say, so finally, the remainder is 3. And we do a connection to the next block of the text. We say something like, what's next? Like, let's calculate the remainder modulo 3 of this number. And we proceed with the next sandwich block. And like the final part of this discussion is fractal structure of these sandwiches. So if we have a bigger chunk of text, we just divide it into bigger sandwiches, each part of which consists of smaller sandwiches. And when we do this, we can naturally go to a thesis of the solution. We just keep a record of the ideas of any single sandwich which we used. So when we do 2 levels of sandwiches, we have just ideas on the ground level, and we can list them, the idea 1, idea 2, idea 3, and so on. And we have like chapters, which are ideas of the bigger sandwiches, or of the bigger of the sandwiches on the bigger level. Basically, that is exactly what you need for writing down the structure of a solution for problems 7 and 8 of the competition. Okay, that was a small recap of what we've done today, and that is exactly the point when we stop this webinar. So if you have any questions, feel free to ask. As you know, the time scales of our competition, they changed, and the competition was postponed to the next year, to the end of January, if I'm not mistaken. Like, you can check it easily on our website. So we will announce some other webinars for some preparation, like with small part of preparation to the Olympiad part, like to the second and third like segments, sectors, parts of the tasks. Like, as I hope you remember that each task consists of 10 10 problems, and first 6 problems are like basic part, and the second and third parts, we call them Olympiad part, which means that you will have harder problems there, which need writing down a proof, or at least thesis of a proof. And for these, you might need these structure ideas. So we will announce some additional preparations to the Olympiad part, at least a couple of webinars. I don't know exactly for now. So keep an eye on the updates, and I wish you good preparation, and I wish you good luck, and see you on the Olympiad. Goodbye, guys.